We're going to work an example here using Legendre polynomials, which also introduces an idea that is actually very widely used in various branches of mathematics, a generating function. And you don't need to know much about Legendre polynomials. Essentially, what you need to know is really that for each integer n, Pn is a polynomial of degree n, and that's about it. Well, here's the problem that we're going to work. We define a function g of two variables, u and x, as a power series in u whose coefficients are the Legendre polynomials Pn of x. And we define the function g for x between -1 and 1 and u between -1 and 1. And the reason is that we can only be sure that the series actually converges if these conditions here are satisfied. And the basic fact that you need to see that that's true is that the Legendre polynomials lie between +1 and -1, provided that x is between 1 and -1. And for larger or smaller values of x, the magnitude of Pn gets larger, and that of course affects the convergence of the power series. So what we have to do is to calculate these partial derivatives here and show that this partial differential equation is satisfied, and we are given that the Legendre polynomials satisfy two identities. The first one here essentially expresses the derivative of the nth Legendre polynomial in terms of undifferentiated Legendre polynomials, and this relation here is the relation between Pn, Pn minus 1 and Pn minus 2 that we'll need in due course. Well, it's pretty obvious how we start solving this problem. It's easy enough to calculate dg by du working from our definition of g there. dg du is just the sum of nu n to the -1 times Pn of x, and the partial derivative with respect to x here is just the sum of u to the n times the nth derivative, times the derivative of p sub n. Now, I've written this equation in the form where the summation goes from 1 to infinity, and that's because p sub 0 is a polynomial of degree 0, therefore it's a constant, so the derivative of p0 is 0, so the 0th term in the sum is 0, so we can just forget it and start the summation at n equals 1. Now, what we want to do is to relate this dg by dx here to dg by du here. dg by du involves only undifferentiated polynomials. dg by dx involves these derivatives, so we're going to use this relation here to substitute for Pn dashed in terms of undifferentiated Legendre polynomials. And when you substitute this identity into this sum here, what you get is that. That's just straightforward trivial algebra. And now we do a bit more straightforward trivial algebra. I just work out x minus u dg by dx, which is really what comes into the partial differential equation that we're trying to prove. We want to show that u dg du equals x minus u dg dx. Therefore, we look at x minus u dg dx, we multiply this thing here by x, multiply it by u and subtract, and we get this bunch of terms here. I'm not going to take you through the tedious but trivial details of that. Well, we've just calculated dg by du to be n u to the n minus 1 pnx, so u dg by du is given by that power series there. And we also calculated x minus u dg by dx to be this horrible looking mess there. And what we're trying to do is to show that u dg du equals x minus u dg dx. But this is a power series in U, and this is also a power series in U. It is the sum of powers of U multiplied by functions of x. And if we're regarding U as the variable for the moment and temporarily regarding x as a constancy, so in these power series, so to show that they're equal, all we have to do is to show that the coefficient of u to the n in the first series is the same as the coefficient of u to the n in this rather complicated looking series here. And that's not that hard. In fact, the coefficient of u to the n in this first series here is glaringly obvious, and the coefficient of u to the n in this second series here I'm now going to work out just by looking at the terms one by one. So in this first term here, the coefficient of u to the n is obviously nx squared pn. Now let's look at this second term. The coefficient of u to the n plus 1 is nxpn, so the coefficient of u to the n is got by replacing n by n minus 1, so it's minus n minus 1 x p sub n minus 1. So now let's look at this term here. Again, that's straightforward. The coefficient of u to the n is minus nxpn minus 1, and finally nu to the n plus 1 pn, the coefficient of u to the n plus 1 is n pn minus 1, and therefore the coefficient of u to the n is got by reducing n by 1, and there it is, n minus 1 p sub n minus 2. So that is the calculation of the coefficient of u to the n in this fella there, and a bit of entirely trivial algebra reduces it to that. Now, this formula here is a combination of pn, pn minus 1 and pn minus 2. But remember, we were given at the beginning of the problem a relation, an identity satisfied by the Legendre polynomials, which relates pn, pn minus 1 and pn minus 2. We can think of this as expressing pn minus 2 in terms of pn and pn minus 1. So we substitute that into this equation, or this formula there, and it turns out very nicely that as well as the pn minus 2 disappearing from this formula here, also the pn minus 1's cancel out, and what we're left with is this. And look, this is lovely and simple. We can factorise npn out of this square bracket here, and what we're left with is x squared minus 1, which cancels out against that x squared minus 1. Therefore, we have found that the coefficient of u to the n in x minus u dg by du is just npn. And that's exactly what we need, because the coefficient of u to the n here is also equal to npn. So we have found that dg by u dg by du equals x minus u dg by dx, and we've completed the first part of the problem. We've shown that the function of two variables g satisfies this partial differential equation. Now, this is the second part of the problem. What we've done so far is rather uninteresting. We've shown that a mysterious function g satisfies an equally mysterious partial differential equation. Now, what we're going to do is to deduce from that partial differential equation that g of u is actually equal to this very simple function here. Well, moderately simple function, 1 over the square root of 1 minus 2xu plus u squared. We need though to, because this partial differential equation here is a bit on the complicated side, it's a type of partial differential equation which you might not have met, and it's not obvious how to solve it. We're going to use the given fact that if a solution of this partial differential equation is 0 when x equals 1, then it's 0 when mod x is less than 1. And I'm also writing down here a given fact about Legendre polynomials which you might not know and which is needed in order to solve this problem. I've drawn here a picture of the XU plane. This region between the blue vertical lines is the region mod x less than 1. That's the region where we're trying to find the value of g of u and x, and what this condition here says is that if we're given values of x on this boundary of that region, then we can find u of x in the interior of the region. So it's a kind of boundary value problem for a partial differential equation. I mentioned this really just to try and make a bit more sense of it. It's not something that's particularly important for this problem. What's important is the technique rather than the concept. Anyway, using these given facts here about this partial differential equation, we want to show that g equals this function here, so we give this function a name. We call it gamma of u and x is 1 minus 2xu plus u squared to the minus a half. And easy differentiation shows that gamma satisfies that partial differential equation, just a case of working out d gamma du, d gamma dx and doing some juggling. We also need to look at what's happening at x equals 1 according to this condition here. So we look at gamma when x equals 1. When x equals 1, this x just disappears. We get 1 minus 2u plus u squared, which is 1 minus u all squared. So to cut a medium long story short, gamma of u and 1 equals 1 minus u to the minus 1. And likewise, g of u and 1 is given by u to the n pn of 1. Here we are given important fact about Legendre polynomials, that Pn of 1 is equal to 1 for all n. So this is just sigma u to the n, which is again the sum of a geometric progression which equals 1 minus u to the minus 1. Therefore, we've shown that g and gamma take the same value at x equals 1. And therefore, g minus gamma is 0 when x equals 1. Also, we've shown that g and gamma satisfy the partial differential equation. Therefore, g minus gamma is also a solution because this partial differential equation here, equation 3, is a linear equation. So, g minus gamma is a function which satisfies the partial differential equation. It equals 0 when x equals 1, and using this fact here, it follows that g minus gamma is 0 everywhere, and therefore g equals gamma, and that shows that this combination of u to the n's and pn's, this power series, equals this straightforward elementary function, and that function is called a generating function for the Legendre polynomials. Okay, so here now is the equation that we've just proved, but it can be derived in other ways. In fact, when Legendre came across these polynomials in the first place in the late 18th century, he defined the Legendre polynomials initially not as solutions of a differential equation. He defined them as the coefficients of the powers u to the n when this function on the left is expanded as a Taylor series with respect to the function u. And why was he interested in this function on the left? Answer, he came across it when he was working on a problem in gravitational force or gravitational potential. So, like so many things in pure mathematics, it arose in the first place through a problem in applied mathematics, in this case a problem in physics. And equation 4 here is useful. For instance, if, like Legendre, you do not define the Legendre polynomials by means of the differential equation, but you define it from scratch by using this formula number 4 here, then you need to be able to define all the properties you need to be able to derive the various properties of the Legendre polynomial that in most textbooks and courses are derived from the differential equation. In fact, it's not hard to use this equation here to derive the recursion relations, the relations between Pn, Pn minus 1 and Pn minus 2, and between Pn dashed and Pn that we use to derive it. So it's a useful concept, this generating function. It's a useful tool in mathematics. Here's another way in which it can be used. It can be used to get an expression for Pn of a rather different form from what we've seen so far. The nth Legendre polynomial can be calculated from this contour integral integrated around any clockwise oriented path that's meant to be a closed curve around the origin in the complex plane, like so. Where does this equation come from? Where does this integral come from? Well, I hope you remember Cauchy's formula in complex variable theory. Cauchy's formula leads to an expression for the coefficients of a Taylor series of an analytic function in terms of 1 over 2 pi I times an integral like this. And this function here, the generating function, is indeed an analytic function provided that mod x is less than 1 and mod u is less than 1. In that region, this is an analytic function of u, and these are the conditions that we were given at the beginning of the whole exercise. So it is an analytic function, and therefore Cauchy's formula for the Taylor series coefficients immediately gives you this beautiful, if I may say so, expression for the Legendre polynomials as contour integrals. Notice that we have here an expression for Pn which makes sense for any value of n, although if n is not an integer but a fraction or an irrational number even, you will have to think twice about the contour integral. But essentially this can be made to work for non-integer values of n, which gives us a way of extending the function Pn to non-integer values of the subscript. Note the difference from the Rodriguez formula expression for Pn, which is Pn expressed as the nth derivative of something. There's no way that you can make that definition of Pn work for non-integer n, is there? Is it possible to differentiate a fractional number of times, to differentiate half a time, or to differentiate something pi times? Well, the obvious answer is no, but in fact the answer is yes. There is a whole theory of fractional differentiation which is quite interesting and a little bit useful sometimes, but that's way beyond the subject of this video. So I'll just end up by saying that generating functions exist for many other functions than Legendre's.